Hello everyone, we're back and we're going to be looking at Clue 7 today. So in Clue 7, we're going to be talking about the mid-ocean ridge. The first thing you're going to want to do is create a Vocabulary 7 page and go ahead and pause the video right now to add these words to it. Before we get into Clue 7, I wanted to do a little bit of review. So just a reminder that divergent boundaries are boundaries where plates are moving apart from each other. Right, you can see in this image here, moving apart. Also a reminder, normal faults are where two areas are splitting apart, and the way we remember that is we say that it's normal to break up, and it's nobody's fault. Normal fault. We remember the tension because it can be a little bit tense after a breakup. Right? So tension stress is that pulling stress. Think of when you pull apart a candy bar and that kind of nougaty caramel center kind of stretches out. That's a pulling stress. And then when this happens at a divergent boundary, the magma from below is able to rise up and fill in that space that's created, and it'll cool and turn into new crust. And it kind of acts almost like a conveyor belt, right? The new crust is here, and it gets pushed further and further out. Further it gets pushed, the older the crust becomes, right? So you get this new crust in the middle, and the further the plate moves out, away from that mid-ocean ridge, the older it becomes. You're going to see rift valleys forming there as well if you're on land. So if you're, let's say, in Iceland, and you were walking along, you would see something like this. Plates on either side, and a valley created where they're diverging. So because the magma is coming directly up, there's no subduction happening, it tends to be a lot lower viscosity. You tend to get shield volcanoes in places like Iceland. So for this clue, we're going to want to look at specifically the mid-Atlantic ridge that runs along here. It divides the Atlantic Ocean in half. And for this clue, we're also going to want to look at specifically what a mid-ocean ridge is, what country lies on the mid-Atlantic ridge, what plates are involved there, and what landforms we can see at the MAR. So we can kind of think of the mid-ocean ridge as this huge, extensive chain of mountains that, for the most part, are under sea level. And you can also imagine them almost like the seam on a baseball, right? They kind of wrap around the earth in the same way that the seam wraps around the baseball. And they're pretty far down. They're not easy to get to. The average height to the tip of the mountain range from the top of the water is about 2,500 meters. So most of them are pretty far below the water level. There are areas, such as Iceland, that rise above. And we know from talking about this in class that Iceland is also a hot spot. So because it's a hot spot, you've got this big plume of magma that's pushing up even faster at this area. So it kind of doubled the size, and it was able to rise above sea level. All right, you're going to want to pause at this point so that you can add these definitions to your vocabulary. Go ahead and do that now. So the theory of seafloor spreading. This is a theory that came after the theory of continental drift, and this was actually after Alfred Wegener had already died in Greenland. Poor Alfred Wegener. And Harry Hess came along, and he really believed in Wegener's theory of continental drift, and he actually provided the how. Remember, Wegener had all this evidence that the continents had moved apart. He couldn't provide an explanation for the how. So Harry Hess comes along and he says, you know what? I think I know how this happened. He proposed the theory of seafloor spreading. All right, so go ahead and pause the video at this point so you can add the definition of seafloor spreading to your vocabulary. All right, and we're going to look at some of the evidence that Harry Hess gathered for seafloor spreading. So his idea was that the formation of new areas of oceanic crust occur through the upwelling of magma at mid-ocean ridges where plates are separating. So this was a new concept, the idea that plates could separate and that you'd get new magma coming up from below, creating new land. All right, so this is just a diagram of how it happens. You can see the magma coming up, new oceanic crust would be created, and you get this kind of conveyor belt moving the land along. All right, at this point, you're also going to want to make a page and pause the video so that you can copy down Harry Hess's evidence of seafloor spreading. Go ahead and pause to do that now. So his first piece of evidence was pillow lava, believe it or not. And it's this molten material that comes up at the mid-ocean ridge and cools very rapidly and forms these pillows. And this was discovered, they sent submersibles down. This was submersible Alvin, and it actually took photographs and video of the magma coming up at the ridges. So you could actually see it as it was happening. The other kind of evidence he found we call magnetic stripes. And they're these big stripes of magnetic polarity that they were able to measure using the rock. And I'll explain that a little bit further, but this is a diagram showing what it would look like. So the magnetic stripe has to do with polarity. Right? So you're going to want to pause to write down the definition of polarity, but it's just the direction of a magnetic field. And the way this works is that the Earth acts kind of like a giant magnet. And the reason it does that is because if you remember at the beginning when we started talking about layers of the Earth, that the core is made up of nickel and iron, these molten metals. And these metals act to create this polarity of the Earth. And it creates this giant magnet. And this magnet is what creates our magnetic north and our magnetic south. It's the reason that compasses work, right? The little needle in the compass will point north. And actually, this sounds a little bit weird, but magnetic south is actually on our north pole and magnetic north is actually on our south pole. And that's why the northern end of the needle points south, because with magnets, opposites attract, right? So the reason that they end up seeing these magnetic stripes in the ocean floor is that when magma cools, it has magnetic minerals in it. And those minerals, just like the needle on a compass, will align with the magnetic North Pole. Well, what they discovered was that actually throughout Earth's history, the magnetic polarity shifts. So today it's what we call normal polarity, with magnetic south pointed this way, magnetic north pointed this way, so our compass needles point north. But years ago, and we see that the last shift was about 7,800 years ago, it was reversed polarity, which meant that magnetic north was pointed this way, magnetic south was pointed this way. So if we had been around at that point and had a compass, our needle would actually be pointing south. And they discovered this because looking at the rocks, they started to shift over time back and forth from north to south. So they ended up finding these stripes along the ocean floor. So if I go back to my image over here, right, so this would be present day, right close to the mid-ocean ridge. If we took a sample of rock here, we'd find that all of the metal inside of it was aligned in the normal polarity, that it was pointing north. But as you move further out, there's a stripe where it's pointing south. And as you move even further out, it goes back to pointing north and then back to south. So you end up with this normal, reversed stripes as time went on throughout Earth's history because the polarity was constantly shifting back and forth. All right, so the next piece of evidence was from drilling samples, and they sent vessels down to take samples, and they found that by dating the rock, that the newest rock was closest to the mid-ocean ridge, the oldest rock was further away, which showed that indeed the plates were moving and spreading apart. All right, this would be the youngest samples of rock taken here, oldest the further out you got. So even though there's new oceanic crust being made and constantly spreading, the Earth isn't getting any bigger. And why might that be? Because in other areas of the world, we get subduction happening. So while new crust is being created, there's always old crust being destroyed. The best example of that would be if the Atlantic is growing and spreading, the Pacific is subducting. It's actually getting much smaller. So North America, we're getting closer and closer to Asia, while we get further and further away from Europe. All right, so you can see here, Atlantic Ocean spreading. Bye-bye, Paris. We get further and further away each year. All right, and finally, remember at the divergent boundary, the landform that we see is Iceland rising up. And at Iceland, it's spreading apart the North American and Eurasian plates. All right, so this has been Clue 7. Thank you, and I'll see you guys tomorrow.